Hello students, welcome to Examinist. So continuing our discussion with particle fields and continuity equation. Okay, so we already studied about continuity equation, and in this lecture we'll focus on a particular derivation that goes as follows. Consider you have a mountain here, okay, and if you are climbing this mountain with a velocity v, then in time dt, how much distance are you covering? In time dt, the distance covered by you is dl. Okay, so what is dl? Dl, that is the distance covered by you in time dt, is equals to v into dt. Simple. Okay, now just draw a line this way and a line this way, and what is this angle? Say this angle is angle phi. Okay, so what is sine phi? Sine phi is equal to perpendicular, which is dh. Dh is the height you moved through in time dt. You see, you went from this point to this point in time dt. Okay, so what is the height you covered? This is the height that you covered. So what is sine phi? Sine phi is perpendicular, which is dh, divided by hypotenuse. For this small triangle, the hypotenuse is dl. Okay, now if you look carefully, dh, that is the height you moved in time dt, can be written as dl sine phi. Agreed? So this is a result, and it can be simplified in this way. So dh, the height that you moved in time t, is your velocity into the time into sine phi. Okay, so remember this result. Now consider the same mountain, but this time you are moving with a velocity along this side. Uh, Let me draw like this. So consider you're moving with a velocity along this direction. That is, you make an angle theta. Okay, so you are not climbing the mountain directly using this particular line, but you are somewhere on the body of the mountain, and you are going in a slanting direction, that is making an angle theta with respect to this particular direct motion. See, this red line is the direct way to the top. Okay, but instead of using the direct way to the top, you thought of let's go to the top using the body of the mountain. Okay, anyways, in this case, can you tell me in time dt how much distance in terms of dl are you going to cover? That is, if you go along this path, along this direction with velocity v, then in time t, how much of this distance will you cover? I mean this distance. If you can look at carefully, then obviously it will be clear that this time dl is going to be v cos theta dt. Okay, where cos theta is the component of velocity along dl. So v cos theta is helping you to cover the distance dl along the direction of the dl. Okay, now my question is, if you are moving in this way, what is the height that you are traveling in a particular time? Okay, so quite easy. You will say, hey, dh is always equals to dl sine phi. Remember here phi and theta are different angles. Okay, I'm not gonna repeat. This is phi, as you know, and this is theta. Okay, so what is dh? Dh equals to, what is dl? dl is v dt cos theta. So write it, v dt cos theta. And what is sine phi? For small angle, sine phi is equals to tan phi. So you can easily write sine phi is dy by dz. So let us see what is dy. So consider this direction is the y direction and this direction is the z direction. So you can easily see that dy is equal to dh, and dy by dz represents the space variation of h. So finally dh can be written as v dt cos theta. Now what is space variation of h? Space variation of h is represented by gradient of h. Okay, so the final result, that is the rate of change of height. That means the rate at which you are covering the height is equal to v dot gradient h. Remember, v is a vector and gradient of a scalar is also a vector, and dot product will give you a scalar or just a number. So dh by dt is v dot del h, or I can say v dot del is an operator that helps you calculate the rate of change of a particular quantity. Okay, similarly, so remember that v dot del is a scale, is an operator. Okay, and we will look at the application of this operator now. Okay, I hope you remember this discussion. So let's go to our fluid. Here you can see a bob. Okay, so it's a small ball, you can say. It's better I call it ball. Okay, small ball of fluid. Now the question is, this small ball of fluid is going to move along this path. Okay, it's going to move along this path. Now my question is, what is the rate of change of pressure this ball is experiencing when it is moving through this liquid? Okay, let's try to understand this. You see that this is the region where the pressure is low, and this is the region where the pressure is high. As I said in the last class, that a fluid has field variables that depend on space and time. We talked about the velocity field, which is represented as v tilde like this. We talked about the rho field, the density field. Here we have one more field operator, which is the pressure. Here you can see that pressures are different at different places. Here somewhere the pressure is low, somewhere the pressure is high. So I can represent pressure as a field variable that depends on space coordinate x, y, and z. Okay, so to answer the question of what is the rate of change of pressure experienced by this small ball of fluid as it moves along this direction, okay, it is equal to, use the operator. What was the operator we discussed? Del dot v. This is the operator, and operate it on P. So you see that this is the rate of change of pressure with respect to time that the liquid ball is experiencing as it is moving through this liquid. Let me tell you that here you see this liquid, this part is say an obstacle, okay, and because of this obstacle in front of the liquid's path or fluid path, there are regions of high pressure and low pressure. Now the direction of gradient of pressure, oh, I made a mistake. This is v dot del, okay. Let us see if we have written the same here. Yeah, it is v dot del. The operator is v dot del. So let's write it. It's v dot gradient of p. Okay, so what is the direction of gradient of p? The direction of gradient of p is perpendicular to the streamline path. This is the direction of gradient of p. Okay, so it's a very useful operator. V dot del tells us now that as the ball moves through this part in time, it will experience pressures with changes. So pressure here and pressure here and pressure here will be different. So the rate of change of pressure that it is going to experience will be somehow dependent on the velocity v and the pressure distribution in the fluid. So here we have the velocity v and this p represents the pressure distribution in the fluid. Okay, so I think it's quite clear now. So we will use this formula to understand Euler's equation in the next lecture.